Alrighty, howdy folks. What we're going to look at today is what's called implicit differentiation, and this is 3.5, section 3.5. Cool. Now that I got that one done, let's look at this. In the previous section we looked at chain rule, right? One version of the chain rule is like this: ddx of f of y, that means the derivative with respect to x of a function of the variable y, right? Isn't that interesting? You're trying to differentiate a function of y, but with respect to x. Well, the understanding is that y is in fact a function of x. Okay, for example, y could be g of x, and so we are looking at ddx of f of g of x, right? That's the composite function. Well, anyway, that happens to be ddy of f of y times y prime. ddy means the derivative with respect to y of that function of y, but be sure to multiply by y prime, that is dy over dx. dy dx is what you must multiply that by, right? That's what we learned in chain rule. And based on that, let's look at a few things. What is ddx of y square? Well, does it look like we are differentiating a function of y, that y square, with respect to x? Yeah. Okay, so what are we supposed to do apparently? Differentiate that with respect to y first and then multiply by y prime. Okay, so y square, the derivative with respect to y is simply 2y, and we got times y prime, right? This is something that you must be quite familiar with by now. Let's look at a few more things. What if I ask you what is ddx of e to the y? You will say, well, let me differentiate that with respect to y first, and dy of e to the y is just e to the y. But because of chain rule, be sure to multiply that by y prime. Cool? I think I got one more example, but this is slightly involved. What if I have ddx of xy square? Understand that y is a function of x. So would you agree that one way to look at this is ddx of a product of two functions of x, right? X itself is one function of x and y square is another function of x. So they are multiplying, so we are looking at the derivative of a product. That means we need to apply product rule. Okay, what's the product rule? The first function times the derivative of the second function plus second function times the derivative of the first function, right? That's exactly what I'm going to write. I'm applying the product rule and saying x times ddx of the second function y square plus second function y square times ddx of the first function x. Now we know ddx of y square is 2y prime. So we have x times 2y prime plus y square times ddx of x is just 1. So we have x times 2y prime plus y square times 1. As simple as that. Now, of course, we can rearrange the terms and say 2xy y prime plus y square. You agree with that? Cool. Now, these are the fundamental concepts that we need for what is called implicit differentiation. So I'm just trying to get you to recall some of the old things from the previous section. Now, what in the world is this implicit differentiation and what do the problems look like? Find dy dx by implicit differentiation given that you have 2x square plus xy plus 3y square equals 9. Look at this one. The thing that we need to apparently differentiate and find dy dx of is something that looks like this. do you notice that this is quite different from how all our functions were so far? What's the difference? Here is the difference. Usually, we have a function expressed in the form of y equals f of x. In such cases, we say the function is an explicit function. That is the key. Up until now, we had things like y equals x squared plus 3x minus 2, y equals e to the x, y equals sine x. So clearly, y was explicitly expressed as a function of x. Y equals something, a function of x. And when you have a function expressed that way, we say f is being expressed, y is in fact an explicit function of x. Okay, we say y is an explicit function of x. However, when we have f of xy equals 0, even that is a function in a way. There's a difference. I'll show you what the difference is. But you could have a function y as a function of x defined in this fashion. And in cases like that, we call it an implicit function. Right? Well, do we have something of that form here? Some f of xy is equal to 0? Now, if you say, no man, we don't have a 0, that's a 9 on the right hand side. I agree. Could we subtract a 9 from both sides and make a right side equal to 0? So in fact have 2x squared plus xy plus 3y squared minus 9 equals 0. Well, now do I have it in the form of f of xy equal to 0? That's the idea. So this is an implicit function. And the question is, can we find the derivative dy dx in such cases? And the answer is yes, we can. And that process is called implicit differentiation. And here is how it works. The first thing we say is differentiate both sides with respect to x. Both sides are what? Our original equation. Okay. And when we do, we got d dx of 2x squared plus xy plus 3y squared equals d dx of 9. Okay, that's what we mean by differentiate with respect to x. Right? Cool. Now, what's d dx of the first term, 2x squared? Simple, 4x. What's the d dx of x times y? Ooh, that we need to be a bit careful, right? We need to apply product rule for that one. So x times y prime plus y times the derivative of x is just 1. So for the second term, please pay attention to this. Would you agree it should be x y prime plus y times 1 is just y? Okay. And then the third term, d dx of 3y squared. No big deal. Differentiate this with respect to y so that you get 6y. Be sure to multiply by y prime. On the right hand side, the derivative is 0 because the derivative of a constant is 0. Yep. And so here we have 4x plus xy prime plus y plus 6y y prime equals 0. Did that help any? What are we supposed to find? We are supposed to find dy dx. Are we there? Yeah, dy dx is nothing but y prime. Look at this equation. It has y prime terms. And so all we need to do is solve it like an algebraic equation for y prime and we are done. So how about doing something like this? Let's pick the second and the fourth term because they have a y prime in them and factor out a y prime. When we do, we get x plus 6y. That's what I wrote. And then we'll subtract a 4x and y from both sides. So that's what becomes minus 4x minus y on the right hand side. Would you agree? Cool. Now can we find y prime? Piece of cake. What do? Yes, you're right. Divide both sides by x plus 6y. So y prime equals negative 4x minus y, the quantity over x plus 6y. Ta-da! So that's what implicit differentiation is all about. Cool. I'll do a few more examples, but that's the whole idea. I want to show you something interesting about this though. Let me actually plot this, and I have done that. When you plot what we have, that 2x square plus xy plus 3y square equals 9 thing, equals 9, it turns out to be an ellipse that's rotated. Okay? Why, how, details let's not worry about the details right now. But it turns out that that implicit function of x is in fact, in this case, an ellipse. Now something should bother you when I show you, hey, this is a function of x, man. It clearly fails the vertical line test, right? If I draw a vertical line, does that vertical line cut the graph at more than 1 point? Yeah, it does. So this is not quite a traditional y equals f of x kind of function. And that's the thing about these implicit functions. They may not pass that simple vertical line test that we usually expect of y equals f of x kind of functions. Alright? But the thing is, you can still find derivatives and stuff like that. And it turns out that if you draw a tangent, why are we trying to draw a tangent to this curve? Well, what was our question about? The question was, hey, for this implicit function, can you tell me what the derivative dy dx is? What is dy dx got to do with tangents? Well, the dy dx is nothing but the slope of the tangent, right? So that's why I drew a tangent here. And you will notice that the tangent is different at different points. Meaning, the slope of the tangent is changing, and the slope of the tangent is clearly a function of x and y. Right? At different points on the ellipse, we have a different tangent with different slopes. Okay. Now, quite interestingly, if you observe, let me stop. I'm trying to get it to look with a zero slope. Okay, that's about zero slope, right? Maybe pretty close to zero slope. Would you say the tangent is horizontal here? Now, there's something interesting that's happening, which we will learn in detail at a later time. Where the tangent is horizontal, that's where the function attains a maximum or minimum. That's another reason why we are interested in derivatives. What is the maximum value of this function? Well, give me a second. Let me figure out the derivative and see where the derivative is zero. At the place where the derivative is zero, that is the slope of the tangent is zero, that is the tangent is horizontal, that's where we are going to have maximum or minimum. All that stuff we will learn more in detail later, but I just wanted to show that to you. Where is this happening? That point C happens to have 0.44, negative 1.77. Those are the coordinates where the thing is. So x value is 0.44 and y value is negative 1.77. Wait a minute. In our case, did we get the slope of the tangent y prime to be negative 4x minus y over x plus 6y. When this is 0, what happens? When would y prime be 0? When the top is equal to 0. Would you agree? When would y prime, when would this fraction equal 0? The fraction would equal 0 whenever the top is 0 and simultaneously the bottom is not equal to 0. If the bottom also happens to be 0 at that time, we have a 0 over 0 that's undefined. However, if we have 0 and a non-zero quantity in the bottom, then that is equal to 0. So what this shows is y must be equal to negative 4x. Right? What did I do? I set negative 4x minus y equal to 0 and solve for y. So that means y must be equal to negative 4x. What happens when y equals negative 4x? Oh, the numerator goes to 0. What does that in turn do? Well, that makes this whole slope to be 0 at y equals negative 4x. Wait a minute. Is that what's happening? X is 0.44 times negative 4 is 1.76. This is negative 1.76. Am I right? 88, 176. Yeah. So, in fact, the thing is, this is rounded. It's quite possible that this is not exactly 0.44. It may be 0.44 something extra, 445 or something like that. But definitely we notice that y value is equal to negative 4 times the x value at this point, and sure enough, that's where this tangent is horizontal. Right? If you didn't understand all this complicated part about the tangent, slopes, and this curve and all that, that's okay. The thing that you definitely need to know is how to do implicit differentiation. All this is just gravy. One more thing while I'm at it. I don't know if any of you, do you know what a cam, C-A-M, cam is? A cam is kind of like this ellipse. So in some machines, wait a minute, there's a good example I can give you. There's something called a crankshaft in a car engine, and you will notice that as the crankshaft rotates, the piston valves move up and down, and on the crankshaft there is actually a cam. There are a bunch of cams fitted on that are machined onto that one. So as the cam rotates, it causes this what is called a follower to move up and down. As the followers move up and down, they open and close the valves of the cylinder in a car. So that's a cam. And in fact, I wish I had this one. So it's possible to imagine that if this ellipse were to be rotating, okay, you can see that a flat thing that is resting on this one would be, suppose I have a flat line, folks, sitting on this one. Would you agree that the flat thing would be going up and down if this ellipse is rotating about this axis? See? And what exactly, how much does it displace? All those things require the concept of derivatives. And when you get into what's called cam design in one of the mechanical engineering classes, I remember in graduate level machine design class that I took, one of the things was cam design. And I needed to apply all kinds of things like this. Cool? All right. Let's move on. With that, where are you? Okay, we went through all of that. Cool. Let's look at another problem. Again, find dy dx by implicit differentiation. Any idea what we need to do? Yep, take the derivative of both sides with respect to x, or differentiate both sides with respect to x. So d dx of the left hand side equals d dx of the right hand side. Cool. First term. Can you tell me what the derivative of the first term would be? Well, that's a product. So that means we need to apply product rule. I don't know what I did. Well, I took the constant outside. Okay. I took the constant multiple outside and then just looked at x times e to the y. And so the first function x times the derivative of the second function e to the y is e to the y times y prime plus second function e to the y times the derivative of the first function x is just 1. Right? Then for the second term, think about it. You try to tell me. First function x square times, would you agree, 3y square times y prime? Yep, that's the second term. Third term, then the second function y cubed times the derivative of x square is just 2x. Right? So that's what I got. X square times 3y square y prime plus y cubed times 2x minus, this would be just 6y y prime. On the right hand side, the derivative of sine x is cosine x, so the derivative of 9 sine x would be 9 cosine x. Now what are we supposed to do? Well, there's some distribution that we need to do. Let's go ahead and do the distribution patiently. Distribute the 3 to both the terms and write like this. And then let's collect all the terms that have a y prime in it and the terms that do not have a y prime on the other side. Cool. So I subtracted whatever I needed to, and so that I have on the left hand side only those terms that have a y prime in it. And on the right hand side, similarly, only those terms that do not have a y prime. Cool. Okay, then what? Let's factor out a y prime. What happened to this guy? Why does it behave like that, man? There we go. We were here. Yep, and then I just factored out a y prime and then divided both sides by the coefficient of y prime. Ta-da! It looks complicated, but my hope is that the process was fairly straightforward. Okay. All right, next. By the way, I like this problem so much that it's entirely possible that I would give exactly the same problem in my differential equations class. In differential equations, you would have something like solve y prime equals this, and so they need to find the solution. So that's how differential equations works. Here we got this and all we need to find is the derivative of it. In differential equations, they give you sort of the derivative and then ask you to find the original function y. Maybe it's implicit. So I try to test my differential equation students whether or not they understand implicit differentiation, and so I pull a problem from calculus 1 and throw it on them. Okay, cool. Next. Again, I think this is straightforward. Same process, differentiate both sides with respect to x. The derivative of cosine of x plus y plus e to the xy blah blah. Okay, tell me, what's the derivative of cosine of x plus y? Any ideas? Well, simply derivative of cosine of x plus y would be negative sine of x plus y to begin with, times the derivative of x plus y itself, right? Chain rule. So the first term would be negative sine of x plus y times the derivative of x plus y with respect to x would be the derivative of x is 1, the derivative of y is y prime. And the derivative of e to the xy on the other hand. Wait a minute. I goofed. Jeez, man. Nope. Oh, lordy. Sammy, what did you do with the... I thought I fixed it. Man, I think I fixed it on my desktop, but I didn't copy the right thing. Ah, crud. Minus 2x. I have to have a minus 2x to correspond to the derivative of minus x squared. Okay. And on the right hand side, this is cool. What else am I claiming? So there should be a plus 2x on the right hand side. Let me fix that guy. I'm sorry, guys. I am really sorry. Plus 2x and blah blah on the top again. Plus 2x. That should fix everything. Let me save this guy. Okay. Back to business. Yep. E to the xy, the derivative is e to the xy times xy prime plus y. Chain rule, product rule, a combination of chain rule and product rule. The derivative of x squared is just 2x. And the right hand side, again, product rule. Look at this. I took the 3x, what? Yeah. 3x squared times the derivative of y squared is 2y prime plus 3y squared times the derivative of 2x. Did I do that right? What the hell is happening to me, man? Y squared times the derivative of 3x squared is 6x. Yeah, that works. Samuel. Okay. It's just like factoring out a 3. Yep, it's... Man, my dog is going nuts outside the door. She wants to come in as I'm recording. Give me half a second. Let me open the door and let her come in, please. Sit, baby, sit. All right, sorry about that. The next thing, I separated all the y prime terms and the terms that do not have a y prime, and then divided both sides by the coefficient of y prime. Cool. All right, so that's how you solve this problem. And one more. I like this. xy equals square root of x squared plus this thing. So what's the derivative of x times y? ddx of xy. xy prime plus y. Whoa, what's the derivative of square root of x squared plus y squared? Square root of something, right? Is 1 over 2 square root of that something. So the first order of business is to say 1 over 2 times square root of x squared plus y squared. And then chain rule demands that you multiply that by the derivative of that something itself, which is the stuff inside the radical. You agree with me? 1 over 2 square root of this thing times the derivative of x square plus y square, which happens to be 2x plus 2y y prime. Again, distribute. Ooh, that's not okay. I factored out a 2 from these two terms, and the 2 and this 2 divide into 1, and so we have 1 over square root of x square plus y square times x plus y y prime. Now separate the y prime terms and non-y prime terms, and then divide. Do you see what I did at this step? Does anybody know what I did? How did I go from this step to this step? Well, I multiplied both sides by square root of x square plus y square. So what happens? The first becomes, this term becomes x times square root of x square plus y square, like here, minus y, this square roots cancel for the next one, so it just becomes minus y. Similarly, this becomes x, and that's a y times square root of x square plus y square, right? So that's the next step that I did, and then divide it out. Good. You must become very comfortable with dealing with all kinds of complicated looking algebraic expressions. All right. Now that thing pops up by multiplying both sides by. That should have popped up right after that. Okay. Next. Ooh. Isn't this interesting? Find dy dx given y equals sine inverse of x. Right, the first question that should pop up in your head is, hey, what's this problem doing in implicit differentiation, man? Right? When I said something like y equals f of x was an explicit function. Y is an explicit function of x. So what is this doing in implicit differentiation? So the thing is, we don't know what the derivative of sine inverse of x is. We don't. I gotta ask you an interesting question. Am I being stupid? What do you mean you don't know how to take the derivative of sine inverse x, man? That's simple, right? That's sine inverse of x. Just like when we say a to the negative 1, that's equal to 1 over a, right? And yes, you are right. A to the negative 1 is 1 over a. It's the same thing, man. Sine inverse x, that looks just like this. So that's equal to 1 over sine x, right? Dang, why is this equal sign so long? Because I'm fixing to make it big time not equal to. Y'all see that? Sine inverse x is not big time not equal to 1 over sine x. Don't ever say that. Same thing with cosine inverse x or tangent inverse x. Inverse functions are not reciprocals. In some weird cases, it turns out that the inverse is the same as the reciprocal, but in general, no. All right, so that's why we would have to resort to a different technique, and lo and behold, this implicit differentiation is precisely what comes to rescue. How? Well, when y equals sine inverse of x, that means sine of y is equal to x. Cool. If y equals sine inverse x, then sine y is equal to x. Does it make any sense to you? Yeah. Let me give you a more concrete example. If somebody were to ask me, hey, what is sine inverse of, let's say, 1/2? Okay. What is sine inverse of 1/2? This is what I'll say to them. Give me half a second. Sine of what angle equals 1/2? Sine of what angle equals 1/2? Well, sine of 30 degrees, or if you express in radians, you must express in radian. Sine of pi6 is equal to 1/2. And so, I can confidently say this must be equal to pi over 6. Right? Now, would you agree this kind of looks like sine inverse of x equals y? Right? With x being 1/2 and pi6 being y. Well, when is this true? Or if this is true, what is also true? Automatically, sine of pi over x must be equal to 1/2. That's exactly what I'm saying in terms of variables now. Cool? All right. So now, once we have sine y equals x, if I differentiate both sides with respect to x, and I get d dx of sine y equals d dx of x. Wait, what's the derivative of sine y but with respect to x? Same, apply chain rule concept. Find the derivative with respect to y first, which is cosine y, but then be sure to multiply by y prime. Right? Differentiate with respect to y first to get cosine y, then multiply by y prime. That's the left hand side. And the right hand side is just 1. And y prime, therefore, is 1 over cosine y. What were we trying to find? Dy dx. Oh, y prime is nothing but dy dx. So we do have the answer, 1 over cosine y. 1 over cosine y? No, we want the answer to be y prime to come out in terms of x. How can we replace cosine y with something in x? Wait. Isn't cosine y the same as 1 minus sine square y? Why did I teach this way? Yeah, this is one way. I'll show you a better way. I'll show you a much better way. Cool. Let's take that sine y equals x. And now, draw for ourselves a right triangle. Cool. And then we'll say one of these angles is y. Because we have sine y, we'll say, let's say one of these angles is y. But remember, sine is, what's that mnemonic? Do you remember this mnemonic? SOHCAHTOA. Sine, opposite over hypotenuse. Cosine, adjacent over hypotenuse. Tangent, opposite over adjacent. So that means when we have sine of y equals x, that means opposite side must have a length of x. X can be thought of as x over 1. And so the hypotenuse is 1. Right? So what did I do? I took this relationship between x and y, that sine y is equal to x, and expressed it in a right triangle. Well, what did the Greek guy say? What Greek guy, man? Pythagoras. If the hypotenuse is 1 and one of the legs of the right triangle is x, then the other one must be square root of 1 minus x square. Right? Cool. Now, looking at this triangle, if I ask you, tell me what is cosine of y? Because we had cosine y there. So what is cosine of y? And you could go, piece of cake. Adjacent over hypotenuse. Adjacent happens to be square root of 1 minus x square. And ta-da! We could have gone from this cosine of y to square root of 1 minus x square that way. That would have been much better. Okay, cool. So now d dx of sine inverse of x, therefore, is 1 over square root of 1 minus x square. A very important result. And in fact, I'm going to derive for a few other inverse trig functions what the derivative is, and you will have to memorize every one of them. Okay? All right, let's move on to what's the derivative of tan inverse x. And the thing is, the procedure is the same for all these stupid problems. Y equals tan inverse x. That implies tan of y is equal to x. Differentiate both sides with respect to x. d dx of tan y equals d dx of x. The derivative of tangent y. Wait a minute. What's the derivative of tangent x with respect to x? Secant square x. Oh, okay. So this means secant square y prime. And the right hand side is 1. So y prime is 1 over secant square y. You see, I went through that quickly simply because it's the same thing. Okay, what is, we need to express this in terms of x. So, there are two ways. I remember the identity secant square y is 1 plus tangent square y, and from that I can get. But as we can do the triangle again, right triangle, call this y. Tangent y is equal to x, opposite over adjacent. So, according to Pythagoras theorem, this must be square root of 1 plus x square, right? Okay, we need secant square y. Yeah, to get secant y, first to get secant square y, let's get secant y first. Secant is the reciprocal of cosine. Reciprocal of cosine is adjacent over hypotenuse, so secant must be the reciprocal, hypotenuse over the adjacent. Would you agree with that? Let me repeat that. Cosine is adjacent over hypotenuse, so secant must be hypotenuse over adjacent, so square root of 1 plus x square over 1. Then, would you agree secant square y will simply be equal to 1 plus x square. I just need to square that square root and the square root disappears. So, I could do that. Instead, what I did is secant square y is 1 plus tangent square y, and tangent y is equal to x, so tangent square y would be x square. That's what I did, but I think I don't know, I'll leave it up to you, okay? I think triangle is a better idea. On a second thought, I should have done all of these with the use of a triangle. It comes in handy when you get to calculus 2 also. There's something called a trig substitution, and there again you'll be using this triangle thing quite a bit. So probably it's not a bad idea to do triangle. Okay, folks? And so the derivative of tan inverse x is 1 over 1 plus x square. Cool. Cosecant inverse x. Y equals cosecant inverse x, and that means cosecant y equals x. d dx of cosecant y equals d dx of x. The derivative of cosecant y, negative cosecant y tangent y, cotangent y. Wake up, Samuel. Negative cosecant y cotangent y times y prime equals 1. So y prime is negative 1 over cosecant y over cotangent y. Whoa, so how do we figure that out? Well, cosecant y is already x. Cotangent y is square root of cosecant square y minus 1. Or we can do the triangle. I'll let you do that. So what should you do? Draw a right triangle and cosecant y equals x. So hypotenuse would be x, the opposite would be 1, and the leg would be square root of x square minus 1. And so we end up with this, the negative 1. Okay. So d dx of cosecant inverse x, folks, is negative 1 over x times square root of x square minus 1. And you got to memorize all these derivatives. Discard that. Why is this looking like that? Why is this guy looking like that? And why is that 6? That should be 5. Cool. We are back to business. The thing is, when I'm saying that I expect you to memorize all of these, yes, you must. However, it's not so bad, because if you remember the derivatives of sine inverse, tangent inverse, and secant inverse, the remaining ones are fairly straightforward. They are related to that. Notice, sine inverse x, the derivative is 1 over square root of 1 minus x square. What's the derivative of cosine inverse of x? Negative 1 over square root of 1 minus x square. So whatever is the derivative of sine inverse x, the negative value of that is the derivative of cosine inverse x. The same thing happens with tan inverse x is 1 over 1 plus x square, the derivative. So cotangent would be negative 1 over 1 plus x square. As simple as that. Same pattern here. Secant inverse x, the derivative is 1 over x times square root of x square minus 1. Negative 1 over x times square root of x square minus 1 for cosecant inverse x. Like if you're like, oh, wait a minute, man. Is that x times square root of x square minus 1 or 1 minus x square? Well, notice for sine inverse x, you have a 1 minus x square. So this won't be the same. Kind of remember it that way. I usually remember it that way. I know that there is an x on the outside, and in addition to the x on the outside, there is a square root of x square minus 1 as opposed to 1 minus x square for the sine inverse x thing. So that's how I remember this. And once I remember for secant inverse x, cosecant inverse x is piece of cake, just stick a negative 1. Cool? Alright. Problem. Find d dx of tan inverse of square root of 1 minus x over 1 plus x. The chain rule. What's the derivative of tan inverse of a simple x? 1 over 1 plus x square. We don't have a simple x, so think of this as u. Tan inverse of u. 1 over 1 plus u square. That means this square root thing squared. Right? Don't stop there. Times the derivative of that u itself, which is what? That square root thing. Okay, the derivative of a square root of something, think of it as square root of u1. Are you with me? We need to multiply this by the derivative of square root of this complicated 1 minus x over 1 plus x. Okay, so think of this as square root of u1. The derivative of square root of u1 is 1 over 2 times square root of u1. So 1 over 2 times square root of 1 minus x over 1 plus x. Right? This u1, please remember, u1 is just the stuff inside the radical. Right? Square root of u1, that means the inside stuff is the u1. So that's why we have 1 over 2 times square root of u1. What else? Oh, be sure to multiply by the derivative of u1. That means the inside stuff. For that, let's apply what rule? How do you find the derivative of 1 minus x over 1 plus x? Quotient rule. Yep, you're right. Lodi ham minus sad low over low 1 plus x times negative 1 minus x times 1, right, divided by square of 1 plus x, and that's what you see. Cool. And then probably in the next step, what did I do? I may have multiplied. Ooh, so that thing goes away. Cool. And ooh, can you tell me what I did here? I know. I looked at this second term here and I wrote it this way. Can I do that? Yep. Think of it as I multiplied both the top and the bottom by square root of 1 plus x. So on the top we have square root of 1 plus x times 1. That's what I wrote here. Over 2 times the square root of 1 plus x cancels out with the square root of 1 plus in the denominator, leaving us with only square root of 1 minus x. So that's what I said here. Times, what is this guy? I just expanded that out and distributed out, and man, I was quite patient here. Now what happened? And I'm not done yet. There are a few other things that are going to pop up. But I'm claiming that the first term is equal to this. Can you figure out how what I must have done to go from here to here? I multiplied by the denominator 1 plus x, both the top and the bottom. So the top became 1 plus x. 1 plus x times 1 is 1 plus x. 1 plus x times this fraction, 1 plus x's will cancel and you get a 1 minus x. Some people don't like the word cancel. I think mathematically people don't like cancel. Cancel means becomes 0. How about this? When I say cancel, if it's a subtraction, addition or subtraction, adding some negative, positive and negative terms or subtracting terms, when I say cancel, that goes to 0. But when I say cancel as applied to division, that's 1. That's the sense in which I mean cancel. I think people are careful in saying that divides into 1 or something like that. That becomes 1. Becomes 1. Maybe I'll try to adopt that technique. Becomes 1. Okay, the next one. Just I wrote that same, copied that same thing. And now what's going to happen to these? Well, there's a negative x and a plus x, and they, I'm going to throw the term cancel. But here that actually means 0, and negative 1 minus 1 becomes negative 2 over the quantity 1 plus x squared. Right? Oh boy, what does this simplify to? Again, this guy, x and negative x, that adds up to 0, and the whole denominator becomes 2. And also there is a 1 plus x here, and there's a 1 plus x, the quantity square here. So, I was even patient. Man, what the hell happened to me? I simplified this and said 1 plus x over 2. And then wrote this, copied this, and times this negative 2 over this. And now did I simplify? Whoa, Nelly. Nope. Oh. what did I do? Okay, yeah, I got it. So that 1 plus x and this the quantity 1 plus x squared. So I took care of that and wrote that as 1 plus x. And I still have that square root of 1 plus x here. And I still have this square root of 1 minus x here. And 2 goes into negative 2 to give me a negative 1. And this 2 is retained here. I think next I recognize that this square root of 1 plus x, and there's a 1 plus x here, that just becomes square root of 1 plus x in the denominator. What? What'd you do there, man? As simple as this. If I have square root of x over x, would you agree? There are many ways of doing this. Yellow. Would you agree the denominator I can write x as square root of x times square root of x? Right? What is square root of x times square root of x? The square root of x, the quantity square. What is that equal to? Well, the square root disappears and you get x, right? So I'm going reverse. And now, can I cancel? Or would square root of x over square root of x become 1? Yep. And so this is equal to 1 over square root of x, right? That's the idea. So square root of 1 plus x over 1 plus x just becomes, in the denominator, square root of 1 plus x. And you tell me, what did I do? Well, is square root of a times square root of b equal to square root of the quantity a times b? So, would we have square under the square root 1 minus x times 1 plus x? Isn't that in the form of a minus b times a plus b, the difference of squares? So 1 minus x square, a square minus b square, or 1 minus x square. That's what I did. Whew. Right? Look at that. So, practice. Work on quite a few problems from this, not just the homework problems, and you should be good. All right, folks. Thank you.